All right, this video lesson is on scientific notation, taking numbers that are very large or very small with lots of zeros in them and simplifying them into a way that's a lot easier for us to write, type, and work with. So scientific notation is when you take a number and you rewrite it so that it's the product of two factors. And it follows a very specific format. And that format is a times 10 to the nth power, where n is an integer. And if you're not familiar with what the word integer means, I'll define it really quickly right here. An integer is a positive or negative whole number. Oops, I shouldn't abbreviate whole number. That's not number abbreviation. So, for example, -2, -1, 1, 2, 3, 4 are all examples of integers, and even 0 is an example of an integer as well. Now that a in this format means something different. A is a number that is greater than or equal to 1 and less than 10. So there's a lot of different numbers that are greater than or equal to 1. For example, 2, 3.74, 8.09 are examples of numbers that are greater than or equal to 1. Even 1 is greater than or equal to 1. But all of these numbers have another thing in common. They're less than 10. So I could have a number that is very, very close to 10, such as 9.9999999, and it meets these qualifications because it's greater than or equal to 1, and yet it is still less than 10. So what we need to be able to do is recognize when numbers are written in scientific notation correctly or not. So let's do that here with these examples. Our first example is 56.29 times 10 to the 12th. Is it in scientific notation? Well, first of all, I need to make sure that my a value is greater than or equal to 1 and less than 10. So my a value is this number here. 56.29 is greater than or equal to 1. However, it is not less than 10. So this is a big fat no, not scientific notation, because a is not less than 10. Now if I look at my next example, 0.84 times 10 to the negative third. Again, my a value has to meet these qualifications. It must be greater than or equal to 1 and less than 10. And 0.84 is not greater than or equal to 1. So this is another no, because a is not greater than or equal to 1. My last example, 6.11 times 10 to the 5th power. 6.11 is in between 1 and 10, and my integer, or my exponent, is 5, which is an integer. So this last example is a yes. This is scientific notation. It meets all of the qualifications. So now, go ahead and pause the video and see if you can correctly identify these as scientific notation or not. All right, I'm going to expect that if you're listening to this, that means you've paused the video and attempted these without me, and you're ready to check and see if you were right. Our first example was a big fat no, because 23.54 is not less than 10. My next example was also a no, because 0.281 is not greater than or equal to 1. And my last one was a yes, because 3.76 is in between 1 and 10, and my exponent, -9, is an integer, so it meets all of the specifications for being scientific notation. So let's try actually taking numbers and writing them in scientific notation with 4 simple steps. So the first thing I'm going to do when I'm trying to write a number in scientific notation is locate the decimal point in that number. Sometimes the decimal will be there and obviously written. Other times we might have to locate it ourselves. Once I've located the decimal, I'm going to move the decimal point so that my number is now greater than or equal to 1, but still less than 10. And this is me writing that mathematically. It might be more helpful if you wrote that in words so that the number is greater than or equal to 1. But still less than 10. However you prefer to write it is up to you. Once I've done that, I'm going to count the number of places that we moved the decimal. Once I've counted the number of places that I've moved the decimal, I can then begin working on the integer that's going to be the exponent for my 10. If the original number I had is larger than what I'm seeing now, then my exponent is going to be positive, a positive integer. If the original number is smaller than what I have written now, then my exponent is going to be a negative integer. Now you're going to want to have two color coding devices out to color code this. So I'm going to highlight and code this information. If my original number is larger, then my exponent is positive. If my original number is smaller, then my exponent is negative. Coding this information in color will help me identify it when I actually apply here. So let's do a couple examples together. Let's try to get 56,900,000 written in scientific notation. The first thing I'm going to do is locate my decimal point. When it's not written, I can assume that it's at the very end of the number. The next thing I'm going to do is move my decimal point until this number is in between 1 and 10. So I moved it to the left several times until it was in between 5 and 6, because then I go from 56,900,000 to 5.69, which is between 1 and 10. Now I move my decimal place. How many places? 1, 2, 3, 4, 5, 6, 7. I moved it 7 times to the left. So my exponent is either going to be positive 7 or it's going to be negative 7. It depends on if that original number is larger or smaller. So 56,900,000 is much larger than 5.69. And when that happens, my integer is going to be a positive number. So my exponent will be positive 7 in this case. Let's try the next one, 0.00985. I'm going to locate my decimal, which has been clearly identified right here, and I'm going to move it until that decimal is in between 9 and 8. So now my new number is 9.85. Now I move my decimal to the right 3 places. So I know that the integer on my 10 is either going to be positive 3 or negative 3. It depends on the size of my original number. If it's a larger number, I'll have a positive exponent. But if my original number is smaller than what I'm looking at now, I'll have a negative exponent. Now 0.00985 is smaller than 9.85. So my exponent is going to be a negative integer instead of a positive. And this will be my scientific notation for this problem. Let's do one more example together. 267,000. I'm going to write this in scientific notation first by identifying my decimal point. It's not written, so it's all the way at the end of the number. And I'm going to move it to the left several times so that it's in between 2 and 6. So now I'm left with 2.67. Now I move my decimal to the left 5 times. So the exponent on my 10 is either going to be positive 5 or negative 5. It depends on if my original number is larger or smaller. 267,000 is larger than 2.67. So this means that my exponent will be a positive integer. So 5 rather than negative 5. Now that we've done several examples together, I'm going to have you pause the video and try these next problems without me. When you're ready to check your answers, unpause the video. All right, I'm going to assume if you're listening to this, that means you've paused and attempted these without me and you're ready to check your answers. So this first one should have been 3.975 times 10 to the 6th power. My next one should have been 3.28 times 10 to the negative 3rd power. And my last one should have been 1.457 times 10 raised to the 1st power. If you wanted to write this last one as just times 10, that would have been acceptable as well. Now that being said, let's say we wanted to take a number out of scientific notation. We would still follow the same steps. We would just have to think about what those positive and negative integers mean for our exponent. For example, if I have a positive exponent in scientific notation, that means that my number is going to become larger when I take it out of scientific notation, and that decimal movement is going to be to the right. Again, I'm going to color code this to code the information for my brain. Positive exponents means the number's becoming larger, so my decimal will move to the right. Now let's say the opposite was happening. Let's say we had a negative exponent rather than positive. If our exponent is negative, that means our number is becoming a smaller number, in which case our decimal is going to move to the left. So I'm going to code this in my other color. Negative exponents indicate that our number is becoming smaller, so the decimal movement is in the left direction. So let's apply this to some examples. My first one, 1.55 times 10 to the 6th. I have a positive exponent here, which means that my number should become larger, indicating that my decimal movement should be to the right. So the decimal in 1.55 is going to move to the right 6 places. So let's rewrite this over here where I have some space. I'm going to take this decimal, move it once, twice, 3 times, 4, 5, 6 times to the right. And all of these empty place values are going to be filled with zeros. Now I'm not going to leave my answer like this because this is really me showing my work. I'm going to rewrite my answer neatly with commas in the correct place. When I rewrite this with commas in the correct place, I now have a nicely written number of 1,550,000. Let's try again with another example. This time I have 2 times 10 to the negative 11th power, which means that my number is becoming smaller since I have a negative exponent. Therefore, my decimal is going to move in the left direction. Now 2 doesn't have a decimal written, but I know that decimals come at the end of numbers that don't have decimals written. So I'm going to show my work over here, and I'm going to move my decimal to the left 11 times. So let's try this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Boom! That's where my new decimal is going to be, and I'm going to fill all of these empty places with zeros. And this is me really showing my work. But I'm going to rewrite my number neatly with a 0 in front of my decimal, because that's proper way to write decimal numbers. I'm going to finish with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros and my 2. And this is my number written in standard notation. Now let's try one more together. Again, I've got a positive exponent this time, so that means my number is going to get larger, indicating that my decimal movement is going to be to the right. So I'm going to take 5.07, and I'm going to take that decimal and move it to the right 4 times. 1, 2, 3, 4. And fill these empty places with zeros. And when I rewrite my number, I'll have 50,700. So go ahead and try these next ones without me. Pause the video, and when you're ready to check your answers, unpause. Okay, I'm going to assume if you're listening to this that you are ready to check your answers. So for our first one, we should have gotten, and I'm going to show my work here as I'm getting my answer, because it's a little bit harder for me to do in my head. 1, 2, 3, 4, 5, 6, 7 times to the right. Fill with some zeros. You should have gotten 64,509,000 for your first answer. For your next one, we should have had 0.00009 0.087 for our final answer. And for our last one, you should have had 0.003002 for your final answer. So hopefully this lesson was clear, a good refresher on writing in scientific notation, and you are ready to move on to the independent practice.